So today we're going to look at our last 6 derivatives that we need to know. Okay, the last 6 derivatives, and that is the derivatives of the inverse trig functions. Okay, and I will tell you that these can be a bit challenging to remember. So I wanted to make some comparisons here, and actually the way this is laid out really helps us do that. You'll notice that our cofunctions are nearly identical. Remember, sine and cosine are cofunctions, tangent, cotangent, secant and cosecant, those are the pairs of cofunctions. And we knew that they were like the sine of x equals the cosine of x minus pi over 2, or pi over 2 minus x. Those cofunctions have another relationship here with our arc, the derivatives of the arc functions, in that the patterns that they have are the same, except for all of the ones that have c, cosine, cotangent, cosecant, are negatives. Okay? So arc sine is u prime over radical 1 minus u squared. Arc cosine is negative u prime over radical 1 minus u squared. Okay? Arc tangent is u prime over 1 plus u squared. Arc cotangent is negative u prime over 1 plus u squared. Arc secant is u prime over absolute value of u times radical u squared minus 1. Arc cosecant's negative u prime over absolute value of u radical u squared minus 1. Okay? So these are just patterns that you've got to memorize. That's just kind of how it is. Okay? Now, if we see this and try to work through some of these. So we have the arc sine of 2x. So 2x is the u. Alright? 2x is our u. And that means we're using this up here. U prime, so that's 2, over the square root of 1 minus the 2x squared. So that's 2 over radical 1 minus 4x squared. Okay? That's not too terrible, right? It's just a matter of remembering the patterns. Okay? By the way, these patterns are on that formula sheet I had given you a while back. Things to know. So, arctangent. Okay? So, arctangent, we're dealing with this pattern right here, u prime over 1 plus u squared. So, the u in this case is the 3x. So, u prime is 3 over 1 plus the 3x squared. So it's 3 over 1 plus 9x squared. Okay? Let's do another arc sine. Just working our way through these here. Arc sine. Get rid of that. We're using that pattern u prime over radical 1 minus u squared. So u prime, u in this case is this radical x. So u prime is 1/2 x to the negative 1/2. So 1 over 2 root x, right? So that is over the square root of 1 minus radical x squared, which is just going to be an x. Okay? So now here, simplifying this, if I have a fraction that's then divided by something else, I can now write this as 1 over 2 root x radical 1 minus x. Okay? You can leave it like that, or we could put the radicals together, make it a radical x minus x squared if we want. We don't have to. And then finally, this last one here, we have the u, arc secant of e to the 2x. So arc secant, we haven't used this one yet. It's going to be u prime. So what's the derivative of e to the 2x?
2e to the 2x.
Yeah, 2e to the 2x over the absolute value of e to the 2x times the square root of e to the 2x squared minus 1. Now, this one we can actually simplify a decent amount here. Okay? What's the absolute value of e to the 2x? E to the 2x, yeah, this is where, again, knowing the range of your functions is really important, because e to the 2x is always positive. So I actually can cancel these out. Okay? Because e to the 2x over e to the 2x is 1. Okay? So now I have just a 2 in the numerator, and in the denominator, e to the 2x squared is e to the 4x minus 1, and that's in my radical. Okay? Does anyone have any questions about any of these? Okay?
How come it's not e to the 4x squared for your time?
Because when you're doing e to the 2x that is then squared, you multiply the exponent, so it's just 2 times. It's not the exponent that's being squared, it's the whole thing that's being squared.
Okay.
So you multiply your exponents.
Mr. Hickson,
Yes?
for the last one, it doesn't have a critical value, right?
It doesn't have...
It can equal to 0.
Oh, yes, this last one here, there would be no critical values there. Well, I should say that it will never equal 0. The only critical value would be the value of x that would make our denominator equal 0, which would actually be x equals 0, because I'd have e to the 0 is 1, 1 minus 1 is 0. So there would be a critical value there, but that's where actually if you think about the domain of your arc secant, remember the domain of arc secant was anything except for the values between -1 and 1. So x can't be 0 anyways. Alright? That's where this kind of gets a little mind-bending. You really got to know your functions and know the domains and ranges in order to be able to figure that stuff out. Okay? We don't get too deep into this. Okay? We do a decent amount with it, but we're not going to get super deep into it with these rules. But it is something we should know how to use.
Into the derivative rules, or even the last lesson as well?
No, these inverse derivatives of inverse functions.
Okay, the last lesson is like...
Yeah, you should know those things well. Okay. Let's try one more. Let's do one we haven't done yet. We want the derivative of, let's say, arc cotangent of, what do you want to take the arc cotangent of?
X.
Oh, come on.
3x to the 5th.
Okay.
Plus 2.
3x to the 5th plus 2. Okay. So, take a sec here, see what you can do with that. You got the pattern up there at the top for arc cotangent. See what you can do. Alright, So here, the pattern was negative u prime over 1 plus u squared. So what's the negative u prime? What goes on the top here?
Negative 15 x to the 4th.
Good, 15x to the 4th over 1 plus,
9x.
9x.
Oh, well, 3x to the 5th plus 2 squared.
there we go. Okay? And then if you want to combine the 1 with that, just so that it all goes together, negative 15x to the 4th, and we'd have 9x to the 10th plus 12x to the 5th plus 4 plus 1, so plus the 5 on the bottom. And that would be fully simplified. Okay? Now, I want to do one more example, and then I want to connect this back. Paul was asking just now about our rule that we had for inverse functions, and I want you to see that that still works, okay? But let's do this real quick first of all. Okay. We want to take the derivative of y equals the arc sine of x plus x times radical 1 minus x squared. Okay, so y prime, and of course we're going to do this in two separate parts. So what's the derivative of arc sine of x?
U prime over
Root.
root 1 minus x squared.
1 minus u squared, and u is just x, right? So what goes on top?
1.
1, okay? So it's just 1, because u prime is 1.
But it's negative 1, right? Oh.
Arc sine, not arc cosine.
And then you do the product.
Okay, and then yeah, we got to do the product rule. So 1 times radical 1 minus x squared plus x times 1/2 1 minus x squared to the negative 1/2 times a negative 2x. Okay, now that looks pretty complicated, but the reality is we can simplify this a decent amount.
Oh,
Okay.
It's gonna end up tying back together. Sorry.
1 over radical 1 minus x squared. I'm going to multiply this middle one by radical 1 minus x squared over radical 1 minus x squared. So the bottom's going to be radical 1 minus x squared. The top is just going to be 1 minus x squared. Okay? And then this, we have the half and the negative 2. That'll cancel out to a negative 1, so we have a minus x squared over radical 1 minus x squared. That's kind of cool how that works out. So now this whole thing, y prime, is 2 minus 2x squared over the square root of 1 minus x squared. And if you really wanted to go further, factor out the 2 on the top, and a 1 minus x squared divided by a radical 1 minus x squared. What does that come out to?
1 minus x squared.
1 minus x squared.
Yeah. Yeah, the 1/2 power or radical 1 minus x squared. Because you have the first power here and you have a half power on the bottom, so you subtract. And it's just 1 minus x squared to the half. Okay? So we started with something looking pretty nasty, but we were able to simplify it to be something rather simple.
If it said differentiate, would you want us to go that far, or would it stop like?
It depends what you gotta do with it. It's probably, if it's a multiple choice, then you might have to get that far. If it were an application problem, you could stop on the first step and plug in a number for x and get your slope.
Like if it was just, I know we don't usually do this, but if it was just like differentiate, could we pretty much just stop anywhere in that last line?
Yeah,
Okay.
yeah. Okay, so let's make that connection that Paul was talking about. And that is with our inverse functions. We said earlier that if f and g if f of x and g of x are inverses, then g prime of x equals 1 over f prime of g of x, right? Let's try this with what we've done, okay? Now, suppose I wanted to get the derivative of arc sine of x when x equals, let's say, a half. Okay? So the derivative of arc sine of x is 1 over radical 1 minus x squared. Okay? 1 over radical 1 minus x squared. So that's 1 over the square root of 1 minus a fourth. So 1 over the square root of 3/4. Okay? Which is the square root of 4/3, which is 2 over root 3. Okay? Or 2 root 3 over 3 if you like. Okay? But let's use this inverse property here. Okay? If I wanted to find this same thing, okay, g prime of a half, then I would be getting 1 over f prime of g of x. So g of x would be the arc sine of a half. What's the arc sine of a half? What is it? Pi over 6? Okay. So 1 over f prime of pi over 6. Well, what's the inverse function of arc sine? Sine. What's the derivative of sine?
Cosine.
Okay. So that's what we're doing right here. So this is 1 over the cosine of pi over 6. What's cosine of pi over 6? Root 3 over 2. So 1 over root 3 over 2 is 2 over root 3. What do you know? It works. Okay? So great connection there. That inverse function rule that we learned before works for all inverse functions, but it does still work here for these. Okay? By the way,
So technically, if you forgot that, then you can just do that.
if you totally blanked on one of these rules and you had to find like what's the derivative of arc cotangent when x is, pi over 2 or something, you could just do it using this rule instead. Okay? It's a longer way around, but it works. So, okay? Cool.